So now we're going to look at multiples of the minimal polynomial. So the result that we're going to prove is that if we have an operator and a polynomial q, then q of t is equal to 0 if and only if q is a multiple of the minimal polynomial. So for the proof of this one, it's an if and only if. So we'll do the forward direction first. Suppose we have that q of t is the 0 operator. So let's see. Now setting that aside for the moment, by the division algorithm, we know that q can be written as s times pt plus r for some polynomials s and r, with the degree of r strictly less than the degree of pt. Okay, so that means then we've got qt equals s of t pt of t plus r of t. Now on the one hand, we are assuming that q of t is equal to 0. On the other hand, we know from the definition that pt of t is equal to 0. Well, not by definition. We know that by, by definition. I was going to say Cayley-Hamilton, but I was getting scrambled. Yeah, by definition. Okay, so then that means that this entire term drops out, and we're left with just r of t is equal to 0. So r is equal to 0, or else we'd have a contradiction. Then for the reverse implication, this one's just immediate basically. So if you suppose that q is equal to s times pt, then q of t is s of t times pt of t, which is, but pt of t is 0, so you get 0. The end. And then we have a quick and easy corollary 848, which is that when we have a complex vector space, then the characteristic polynomial has to be a multiple of the minimal polynomial. And so this is saying the characteristic polynomial is a multiple of the minimal polynomial. And so there's nothing to that one. It's just immediate from what we have above, but it's a handy observation to make for when you actually go to compute the minimal polynomial of a given operator, because you can start then with the characteristic polynomial and then say, okay, so are there any factors that don't need to be here that we can cancel off and still get the minimal polynomial?